So welcome everybody. I'm Ange Albertini, and I will talk about the PE file format, the Windows executable format. And I'm the author of a website called Corkami, where I share my reverse engineering experiments, and I try also to do visual documentations. So the agenda for today, I start with an easy introduction, explaining what's the PE, and then what there are problems about it, and what was my approach to tackle the problem. Then stepping up, just an overview of the PE file format. And then I'll enumerate a few classic tricks that maybe most of you have heard of, and then show some new tricks. So I'll just speak about the PE file format, PEs, which is portable executable file format, which is based on the common object file format from Unix. So, oops. Oh, missing slide. Sorry. Oh, missing slides. Okay, there's a missing slide. Weird. That's a very bad start. PE files are used everywhere in Windows, whether it's for executables, libraries, drivers, ActiveX, and whatever. And there are many, thousands of them in overall the system for many functions. So, for example, this is an example of all the DLLs that are loaded on a freshly installed Windows 7. And it's not just used for executables, but it's also used for data storage, because via resources in a PE file format, you can very easily, via 3 API calls, access the resources. So the Windows system is using them everywhere, whether it's for icons or a string for localization or even keyboard layouts. So those files, all these examples of files, they don't have code, but they are still PE files, and they are used in the Windows system. So basically, PE file is really the universal Windows binary, whether it's for executables or for data and everything. And it's been so since 1993. PE files is even used in other systems like Xbox, EFI boot, and other Windows CE, but I don't cover them. I just cover the Windows part. So if you need another introduction, a gentle introduction to the PE file format, I made a poster at that address. It's been quite well received, 30,000 downloads. I think it's available in 8 languages. And I just made myself a simple PE, and I show and dissect, and I explain the loading process and everything. Not too complex, but feel free, if you're interested, to download, print it yourself. So the problem is that Microsoft has an official documentation, but this documentation is extremely small, very succinct, and at best it can be seen as a gentle guide to explain the standard PEs, which means it has a very weird way to explain things based on the section names, which are absolutely not relevant, which means as soon as you have a simply malformed PEs, then this doc is quite useless. And I'm not talking about advanced malformation. So it's really, there are other documentations naturally, but this documentation is a shame? I don't know. It's far from complete. So the problems that it creates is that, well, first, with some small malformation, you can crash the OS, or you can crash security tools. So for example, that's Commodore Security crashing on a file with a weird image base. But all those files work, but they can crash the OS, crash your security tools, which is not good for PR and users. Another problem is that it can be also painful for developers. So that's Windows App Locker, which is failing to recognize a valid executable. And the problem was that it's a compiling environment that is not Visual Studio naturally, but all the files that were generated with this compiling environment were rejected by App Locker because there were some details that were not in the official Microsoft documentation. So it can be even a problem for developers. Any developer using that framework would not be able to use App Locker because of gray area in the PE file format. And then another problem you face with malwares and security tools is first being able to distinguish between the corrupted files, because it happens all the time with downloads and stuff, and a malformed malware file that is working and malicious. So it's very hard to distinguish. So you can escape detection and evade security measures by tricking tools doing this. And then, so this, for example, is a simple PE file, well, simple, that is not seen as a PE file, but as an old executable style. And then if you get crazy, then you can, how do you say, VirusTotal thinks this is a PDF, so which means in one security tool, the file might start being scanned as a PDF, and then the PDF part is clean, okay, and it may totally ignore the malicious PE part. So another problem for malicious, with malwares. Then you can fail automation systems. So for example, it's a simple example where with just patching 1 byte in a UPX file, then the UPX will fail to unpack it. It's quite a lame example, but I still see a lot of, write-ups where they use actually UPX to unpack UPX, which is like kindergarten unpacking. And but this means that with just changing 1 byte from a standard file, you could fail automation methodology. And then the worst consequences are you could fail even the most advanced tools such as CFF Explorer, IDA, or Oli Debug. In this case, even an advanced malware analyst or reverse engineer might just fail being able to analyze the file, which is not nice. So many bad consequences, whether it's for users, developers, or automation, and even advanced researchers and malware analysts. So my approach, instead of most write-ups out there, most documentation out there about PE file format are just based on what exists in the wild. So basically, they are just covering what's existing yet. And basically, it's full of, I've never seen that used ever before and so on. So basically, maybe they wait for the next virus writers to actually implement that, and then you discover, and maybe it's too late for your tools, for your knowledge, and so on. So instead of that, I started a very kiddish approach where, well, you give Lego to a child, and they build and they learn the rules by themselves, seeing if it holds or not. So I do that, reading the docs, reversing the loader, and seeing if this is actually how things works. So of course, this is my kind of Lego, low-level Legos. And then, well, it's a bit like this. Of course, not with Lego. It might be difficult to see if it executes. But I do the same with Legos that I would do in assembly. So I create entirely manually, exactly like with Lego blocks, executable files. And in the end, you build up, and in the end, well, you get a complete executable. That's a complete executable, and that's the equivalent in Lego. So just with a few blocks, you get something that is executable, and that might also fail tools and antivirus or whatever, so security softwares. So I started that research long ago. So and basically I built hundreds, 170 proof of concept that I share on my website. And I also created a summary page, pe.corkemy.com, where I try to gather all my findings. But usually my proof of concept set is more advanced, and it's really exploring things that are usually not covered by already existing files. So just exploring slowly every aspect of the PE file format and sharing for everybody to test, study, and so on. So now I'll start an overview of the PE file format. So PE file format. So this is a file itself. You have the PE header at the top, and then the PE header defines a whole area that could be considered as a PE file, and at the bottom you could have some extra area, which would be the appended data. This is not loaded in memory. Then on the PE file itself, you have the header, and then the sections. Basically, the sections are all the part of the PE file that is not the header, so it could be code, imports, data, initialized data, and so forth. And then you have the header. So originally, the top of the header is a DOS header, which was first used by Microsoft for IBM in IBM PC-DOS 1.0 in 1981. So even before MS-DOS 1.0, so way before Windows. And then they had the opportunity to add another kind of headers. So this could be a portable executable. At this stage, it's still a DOS executable. It's nothing for nothing of a PE or whatever. And then you could add another kind of header. So it could turn it into a new executable, linear executable, and portable executable. So then, depending on the signature here, you would have a different kind of header and different kind of file entirely. But as I said, here I could just cover the PE file format. So then it starts with the PE signature. Then you have the file header, which is always there. And then you could have optional header, which is optional. It's not present in object files, it's only present in executables. And you can have a section table. The file header is the one saying, will there be an optional header? Will there be sections? And at the end of the optional header, it's a bit special, but you have an array, which are the data directory, but each of the first 16 elements have a very completely different use. So basically you call them data directories usually, even though they are initially the same structure, then their use is totally different. So DOS header is completely ignored when you're loading the file as a PE. If you're loading if the PE part is corrupted, or if it's really an old DOS format and you have a Windows, a 32-bit Windows, so even on the Windows 7 32-bit, this part will be used. Otherwise, it's totally ignored by the PE loader. So you just need the MZ signature, and then at the end, a pointer which will point, it's an offset, to the PE header. Then the PE header, the file header, the first part of the image entity headers has a few stuff. So for example, here it says it will be Xbox, whatever, but we are only interested if it's 32-bit or 64-bit now. This will say how many sections there will be, if any. And then size of optional headers will actually say where the section table is, and some characteristics to say if it's an executable or a DLL. There are other stuff, but usually not important. Then the optional header is big, but many of the elements are not so important. So mostly important where code starts. It says image and address of entry point. Image base and section alignment give you the geometry of the file where stuff are aligned on the file. We'll see that later. Size of image declares how big the file will be in memory. Subsystem says if it's a driver, command line. And then the data directories with a counter for them. The data directory, they are complex themselves, we'll see them later. So first the sections. So after, you have the number of sections here. Size of optional header will say where the section table is located. So just following that, well, pointed by size of optional header, the section table with, more importantly, where the section, so the section says which part of the file will be loaded in memory and with which attributes, like is it writable, is it executable. And so virtual address is where it will be loaded. Pointer to raw data means where it is in the file as an offset. Characteristics means is it readable, writable, executable. So here is an example where here you have the representation of the file and then what it will be in memory. So the loader determines an image base and initial image base, and from this point on everything is relative to this image base. And then for each section, pointer to raw data, size of raw data is read and loaded in memory at the virtual address, and the virtual size you always bigger or equal. Then it will be full of zeros, extended with zeros, and numbers of sections here is determining. So it's doing this for the number of sections, and altogether this is the size of image. Now the data directories. Well, the elements of the data directory, but all of them are completely different. So first, you have the export and the imports. We provide communication between the executables and DLLs. Then resource is where the second one, if you count this way, is what will provide resources like icons, manifest, version information. Security is where you have the digital signature. It points to where the digital signature is in the file. Exception is used in 64-bit mode for exception handling. Relocations, I'll talk about them later, but it's when the file have to be relocated in memory. So this is information to know how to perform that. Debug is obvious, is only present when you compile with debug. Copyright or architecture is useless. Global pointer was only used in Itanium for, Itanium structure. So it's the relocation equivalent, or Itanium is not used on x86 and 64-bit. TLS is important because it can be code that is actually called before the entry point is called. Load config is used for the safe structure exception handling implemented by Visual Studio compilers, but it's not a p-loader structure. When you have this, it is the file embeds extra code from the compiler. Bound imports is just to speed up the imports loading. Instead of performing lookups with the exports, then you can store the imports so that the actual value that will be loaded in memory to speed up things. IIT, import address table, is not really important only with files without section, but it's just a highlight of the imports themselves. Delay import is another compiler mechanism that is totally ignored by the loader, but it makes the compiler able to not load the file at the start of the execution, but on demand. And COM descriptor or CLR descriptor is used for .NET. And the last one, well, it's never used except it's known because it's used in AsProtect and ASPAC, but it's not used, it has no meaning for the loader itself. So export and imports are the way, the pipeline between a call from the API for an executable to the DLL. So exports, you have 3 lists. So first you declare the name of the DLL, how it's internally. I don't think it's relevant. And then you declare an amount of functions and names which kind of define the export name, which means an address, a name, and an ordinal. Imports, so first you have the descriptors. It's a list of descriptors. Typically, it's 1 descriptor per DLL. So basically, for each DLL that you want, you will have 1 descriptor. Well, actually, it can be wrong, but that's usually the case. And then you have a pointer to the DLL name to be loaded. And then you have the 2 lists themselves, the null terminated list of pointers. And initially, they point to the actual name of the API to be loaded. And then this one, once the file is loaded, then it will it will be overwritten with the actual address in memory. So this kind of defines the import address table in memory. And the other data directory, which is IAT, is concerning this, which means set this as writable for the loader. Otherwise, the write would fail when the imports are resolved. Relocations, standard PEs and DLLs have a standard image base. So basically, when you have 2 DLLs with the same image base, there could be a conflict. So in this case, the OS needs to say, no, not that this image base, but another one. And all the absolute address in the code or in the data will have to be updated. Most of the address in the header are actually relative, so that they don't need to be fixed, but all the absolute address need to be fixed. So basically, it's a set of tables that needs to say this offset. For example, here it's an absolute reference, absolute address. Then you need to fix that because the image base will be changed, and there's nothing anymore at this address. So you have the whole directory. Then you have a set of blocks, and for all the blocks, because code is usually in blocks, and then it defines the start and the amount of relocations here, and for each of them it decides which kind of relocation at what relative offset from the start of the block. The resources, it's file structure, so it's recursive, but typically it's used with only 3 levels. So you define among the important things, so you have the same structure repeating over and over, but by standards root type language, and then the results themselves. And then it just declares the number of named entries first and ID entries, and then it points to the next one and so on. So it's like a file structure, but by standard with 3 levels. And the TLS, very simple structure, even though the TLS itself is quite a pain to understand fully. So basically, you have a list of callbacks, and each of them will be called one after each other before a thread is started and after a thread is terminated. So this means there is code, there's life before and life after death or something like this. And here a small address of index, which will be a pointer that will be overwritten on each TLS load to just know which TLS you're currently executing. So first, I'll show a few classic tricks that I keep being asked about. So usually known in the malware and reverse engineering world. So first, it's not really a trick, but it can already fail some tools. The maximum number of sections in Windows XP is 96, and then from Vista on, it's 64K. So simple files, they work, but good enough to fail only debug 1 and 2. Well, it doesn't fail, it just gives this funny error message, but after it works, but it's quite slow. So it could also be a kind of DOS on tools and security tools. Then one of the biggest problem with the official Microsoft documentation is it defines PEs by their section. And actually, when a file is loaded as a driver, you have this requirement of file alignment being small and equal to section alignment, which means each of the section is identical physically and virtually. And basically, it means that all the file is loaded as is. And it means that actually the section table is more or less ignored. So you can have no section, or like previously, this is another example of the case of section table, sectionless low alignment. Because even though there are 96 sections, well, they are quite obvious corrupted. I hope you can all see. Can you all see the numbers? So this is a working section table, but basically it's ignored. But because of the low alignments, this is all ignored and the file is loaded as is in memory. So another known malformation of the PE file format is the tiny PE files. So basically it implies because the DOS header is mostly unused, you start putting the other headers inside the DOS header, and then you just make sure that at the value for the pointer to the PE header, it corresponds to section alignment that works. And then the other trick is that the optional header is truncated to the last important value. It's actually truncated even before his. It's a word, but you only need the first byte to be defined. So by doing this, you can have a 92 bytes PE file. Actually, the original tiny PE by Alexander Sotirov had a section table, but it's not required at all. So these are the tricks of the tiny PE files. The thing is, after XP, so for Vista and further, it doesn't accept anymore to have a truncated optional header. So you cannot have an optional header too close from the end of the file. So basically, it might still work, but you just need to add some stupid padding. I mean, full of zeros. So in this case, under Windows 7 64-bit, the smallest executable file is 278. But it's exactly the same structure with just added padding up to 268 bytes. Another known trick and funny from reversing labs is dual PE header, or a folded header. I call it folded header. So basically, you extend the file header, you put it further by extending the values, so that it's almost aligned to the start of the section, so that the data directories will be at the start of the section. The thing is, the data directories are only used once the file is mapped in memory. And the trick here is that actually, so basically the mapping will happen. Oh, this is checked, this is checked, this is checked, but this is ignored. Then the file is mapped, then the section is loaded at this virtual address, and this will overwrite the fake data directories. So basically you have the real part that is here and the fake part that is completely ignored. So you have to, and of course you could have another fake header here, but it would be ignored. But the data directories themselves, they will be taken into account once the file is mapped in memory. And then if your tool are not aware of that trick, then you can practice and do some ASCII art or hex art with the fake data directories. But of course this loads because the real ones are just after mapping, before taking into account, overwriting the fake ones. So ASCII art with data directories. Another known trick, but not so well, another already documented trick, but not so well known, and it's quite worrying. It was documented by Skywing in 2009, I think, is that on DLL main, you have a parameter that is LPV reserved, which means no documentation. And it's actually quite worrisome because, so it's only on static DLLs. And this is actually a pointer to the context of the future PE files being loaded. So the PE is being loaded. It's not already started, but the DLLs are mapped and the DLL main is executed. And they already have an access to the context of the future executable to be loaded, which means if in your executable you have a bogus entry point value, and in the DLL main you just check that you're attaching at the start of the load, then you access the context, and then you're changing the future IP because the future EIP of the entry point is already there, so you can modify at will. Here I just took a simple minus addition, but basically it means as soon as a file has static DLLs, which is most of the time the case, then the entry point can be completely modified by the DLL. And Yoru, he actually extended that and he said, because you have access to the context of the future thread, you can even start setting debug registers and so on, or changing the values. So it can be a nasty anti-debugs and so on. But it's weird that the DLL is being loaded, the P is not started, but the future value of the entry point is already there, and you can freely modify it. So now a few new tricks. So let's start simply. I saw that in the characteristics of the file, you have one that says, is it a file is 32-bit? And first of all, well, it's valid for even for 64-bit. Okay, thanks for the logic. But actually, it's not used at all. So even if the file is 32-bit and this characteristic is not set, well, it works. So why is it there and it can be for 64-bit and why it's actually not even used for 32-bit? I don't know. Another funny one, similar in the characteristics, is that if you load the DLL statically and you don't set it's a DLL, well, it still works. The export work. But one thing is funny is that DLL main will not be called, so the entry point value can be totally bogus. And so you have a file that you is loaded statically by the imports. That is a DLL because you can use the export, but it doesn't have the DLL flag and it doesn't have a DLL main. And then you encounter a problem because OLEDebug relies on that flag to say if it's a DLL or an exe. So OLEDebug is unable to debug it because it's not an executable, it doesn't have an entry point, but it doesn't have the flag of DLL set. So it's in the in between of reality. Of the possibilities, so OLEDebug is not able to open that. Fake entry point completely ignored and not set as a DLL, yet works fine. Another trick that still works on IDA 6.3 and Hue and so on is that in the import descriptor, only the last two elements need to be defined. So the first ones, they can be zeros, and those ones just need to be present. So the trick here is to put it in the virtual space between the header or between two sections. So this will be loaded to space that will be filled with zeros. But in this file itself, in the offset, it's pointing to an address that doesn't exist yet. So basically, IDA fails to understand what it will be. It's just a printf and it's just exit process, but IDA doesn't know. Here it thinks it's a byte plus C1, and here it doesn't know what to. It just doesn't understand that there are imports there, and it also fails Hue and so on. So it's still a simple trick, but no more imports. Another advanced, import malformation that I did is when you start putting various import structures inside the, inside the other structures. So basically you have one descriptor and then you have the terminator. So the descriptor here, this part here, is not relevant for the descriptor itself, but, it's pointed as a import address table. The thing is, because this is also a pointer, the loader could think this is an import address table, but it's not the case. So they think it's corrupt, but in the loader itself, even if this is absent or corrupt, or even if it looks right, but in the end it's corrupt, it's ignored. So basically, this structure is breaking the loading, and then you can actually put, this is terminator, supposedly it's full of zeros, so 5 double words set to zeros, but actually, what it only matters is either the pointer to the name or the first thunk is set to zeros. So here I put the DLL name and I set the import name table here inside the terminator, but it's still seen as a terminator because the last double word is seen as zeros. This still breaks IDA 6.3 and other stuff. And also another simple trick is that, from Windows 2000 on, you don't need the extension. And maybe you don't, on XP, you can also append dots here. You can have, so msvcrt.dll ... is seen as a valid DLL, even if the file cannot have such a name, and it's loaded. So you can fail also some heuristics, because under XP that would work. It doesn't work under 7 anymore. I skip Vista. A simple, one thing that is not usually played with is the exception tables, because under 64-bit, because before you could just set FS, play with FS and set things directly in the code, but in 64-bit, they are done in the PE header, in one of the import data directories. So actually I made a simple example because it was much simpler than I thought, and you don't need complex mechanism to set exception handling. But my biggest surprise is that if you change on the fly by the code the value that is in the header, in the, in the handler, if you modify on the fly the handler value that is in the header, then it's correctly taken into account, which is weird because it was supposed to bring more security. So I would assume that the OS was you need some API calls, or the actual value being used by the OS would be somewhere else in memory. It would be a copy, but now it's still the value that is in the PE header. So you can still modify on the fly exception handler in 64 bits, or you can do it statically like some file infectors do. I play with relocations. So first, relocations are not used when you actually don't need to perform them. So if you enter bogus values here, then some tools might just crash because they start parsing it, which is common for tools to actually try to parse everything. Another funny trick, actually it's already documented, is that if you perform a relocation on image base itself, image base is decided by the OS itself. So usually, how do you say? So you wouldn't modify the image base yourself because the OS already modifies it, decides what value it will have. But then once the image base is changed because of relocation and you perform a relocation on it, it will actually affect the value of the entry point because it's a relative value, and the new value of the image base is actually performed to calculate the value of the entry points. So basically, if you manually perform a relocation on the image base itself in the header, then you need an extra delta. So here, statically, the file would have a wrong entry point, but because of this relocation, it's fixed by the OS. Actually, when you start looking at most documentations about relocations, maybe I zoom it a bit, they only mention, most documentation only mention the standard relocation, the high-low one, and the absolute one, which is just here for padding. So basically, most documentation will say high-low, the standard delta, image-based delta one, and this one. All the rest is just ignored. And then I was surprised to see that MIPS and all these odd systems are still present, whether it's under XP, Windows 2000, or Windows 7. And what is funny is that you have those two types that are just ignored, like how do you say, the absolute one. Then the type 8 is rejected. Okay, who knows? Then you have MIPS relocation. Even if your processor and the P are x86, then MIPS relocation are performed. And there are other types. So low is not used, and low is absolutely not used because the image base are rounded, have to be rounded. So low doesn't do anything. Actually, so it was the same under XP, but actually in Windows 8 there was some cleaning, so there are no more IMIPS and IA64 relocation. But since XP in Windows 2000 until Windows 7, there were a lot of odd relocation formats, and let's take advantage of them. So first of all, if you type 6, as I showed, so type 0 is for padding. Type low actually doesn't do anything because of the round values of image base. And these twos are also not doing anything. So basically, if you set them on the entry point, all those types will do nothing. And you can see this says unknown, but it actually will do nothing. Then you can actually set a fake relocation on a value that is not taken into account by the file itself. So this is a single proof of concept that holds all these tricks together. So then you can set all the relocations types. What is important is that high edge, the type 4, actually requires a parameter. It's the only relocation that the next entry is a parameter for high edge. So this, here basically you can set any values, and actually there's a bug in Windows and the parameter is completely ignored. So here you can set a value, and here this means wrong parsing of the location. Because if you had a type 8, which is the rejected one, then the loading would fail. Then relocations are actually performed on the fly, and you can perform relocations on themselves. So here, this is a simple block that will actually modify something. I even use the MIPS relocation, and this is this block here, and this block here will actually fix the next block length. So basically, relocations can apply to themselves. The consequence of that is that if you take the latest IDA, first you have some error messages, and even if you relocate manually, well, because of this, IDA just has no idea what the final code will be, but because the future image base is predictable, and you can set everything, because this last block here is actually generating the code with relocation, then once it's loaded, then you have perfectly working code. The thing is, if you wanted automated static analysis, failure. Peter Ferry documented most of the values that are possible in each element of the PE header. and it's a very valuable document. And I started to take that into account. So this is a working file, and if you can see, I set it most values with completely bogus values, FF, and of course, it just works. So this can really crash many tools because I really set crazy values. And then, so you can either kind of fuzz passes and fail them. That's a side effect. Or you can put some code. So I did a small example where this is the PE header, and actually the whole PE header is executed. And for example, this here, which is some not so important values, is actually FPU code. So my code is not important, but actually the whole PE header is executed. And so it goes execution through the data and so on. It doesn't jump through. Another much more practical and nice example is this demo by Mentor from TBC. So it's a 1 kilobyte demo. So it's pretty impressive for being a 1 kilobyte. And actually the PE header is the Packer code. Cannot see well. Well, you can see that on my website. And I documented with authorization the whole code, the whole PE header. And the Packer code is in the PE header, but he's cheating a little because he's jumping between blocks, while my example was there. But this is an actual Packer in the PE header among all the values and stuff. And this is quite impressive. And the demo itself, well, it rocks because 1 kilobyte, nice 3D effects and music. Good stuff. Amazing. Okay. I started recently playing with .NET files. So when you load the .NET file, the file is loaded as PE. Then there is an import to MS-Cori DLL. Then the MS-Cori will actually check the PE file again from a .NET perspective and parse it again. It's actually more tricky. It needs more specific things to be right. So for example, this is what is important for the PE files. Just need the imports. Then the .NET needs one relocation on the entry point, and okay, and then the actual .NET header. The thing is, this value is set by the amount of data directories is set by number of RVAs, and the .NET loader forgets to check the actual value. So if you set it to 2, then .NET will still work because it thinks it's big enough to check the data directories, but both IDA and CFF fail to see it as a .NET file. So this was fixed last week, but this is actually already used in the wild by malwares, and so suddenly reflectors, IDA, were failing to recognize .NET files as .NET. Not very important, but just for fun, I made a PE file that prints itself. So it prints its own source. So when you execute it, the source is actually in the file itself. So with ASCII tricks and so on, it's printing its own source in the PE file. Or if you type it, it also works, and you see the source from the file. This is another file that I did. So basically, this is the PE file. And okay, well, the wheel. Oh shit, it's good. So basically, this is the PE file. If you add a PDF signature at the beginning, it can become a PDF and the HTML. Then PK can become a zip also, and you can have a Java class inside. So basically, this is a file that works as a PDF, as a zip, as a Java, and HTML with JavaScript. And I added more tricks so that it's not, the CRC here is invalid, but it works. The PDF here is invalid for standard readers, but it works without errors in Adobe. And because I had full control of the structure, instead of putting the PDF and stuff, then I made like this. So for example, a part of the PDF is inside the Java class and so on. This breaks some loaders. Thank you. Oh yeah, I also throw in some undocumented opcodes in the PE files just to fail WinDBG and so on. So, conclusion. Oh, sorry. Windows executable format is too complex. Microsoft doesn't cover much. But there are new tricks, little tricks every day, sadly. So if you want an easy poster introduction, this address. And if you are serious about PE files, this address. Any questions? Can I start? Bonus? Yeah? No questions? or where you can reach me by email and so on. So bonus, why not? If you're using a 32-bit OS, then the old Windows binaries are still executable, not the non-PE ones. So usually the DOS stub is just about printing something and exiting, but actually the DOS stub has many capabilities. So this is this is a file that is actually a corrupted PE with a DOS stub that will actually repair itself and then execute itself again. So it's weird if you think about it, because this is executed by 16-bit code, and this is 32-bit code, and it also works in Windows 7 32-bit. So you can escape network detection. The thing is, the change is done on disk, so at this moment it could be caught as a PE file. But if you think a DOS stub could be innocent, then it's a problem. Actually, Farbrauch did a 33 bytes demo that is visual and has color effects. So basically, you can replace the DOS stub with this. So instead of having the crappy message, you have very nice full screen animation. Awesome. They should be hid by Microsoft. And another trick is that for the DOS format, you don't need actually the MZ signature. You can have a ZM signature, which is good to evade other detections. Or you can have a COM file, which is even before the exe format existed. So this is a headerless COM file format. And you can use Yusuke Hasegawa encoder. So it's a symbolic encoder, so it's better than alphanumeric. This is an executable file, and this is a COM file that, when executed, will drop a PE and execute it. So nice if you need to type a PE, this works. Still under Windows 7 32-bit. A funny trick I saw is that the bitmap fonts are still the same format, very old format in the Windows 7, since Windows, Windows NT. No, yeah, Windows NT 3.1. So basically, this is not PE files, but it is a new executable file format. And so this file format is from 91, sorry, 91. And the data inside is from 84. And if you go in the properties, this is parsed. So this means in 2012, Windows 8, because it's also true in Windows 8, Windows 8 is still parsing a file format, a 16-bit file format from 85, containing 84 data byte. So if someone finds a vulnerability in that, you can imagine somewhere in the code, in a comment, this is really a 16-bit file format, don't change that. And if someone finds a vuln for that, it's awesome. And also, if you open those files, which are new executable, though before P files in IDA, it fails recognizing anything. And another one, just because I also like that, the opcodes. I found out that lock is usually triggering exception in many cases, and the OS is interfering with that and has already a history, I mentioned that last year in Hash Days, of history of being wrongly handled by the OS. And this one is really funny under Windows 7 64-bit. So this lock prefetch should fail. And if it fails, it should trigger an exception. But here, it doesn't trigger an exception. It just fails silently. So if you have this and you start running, nothing happens. And if you pause, you are actually here. And even funnier, it has been patched by the OS. It doesn't trigger an exception. It cannot go further. So the file is like stuck. It's it's usually the OS doesn't patch opcodes that you type yourself, and either they run, either they trigger an exception. But here, Windows 7 64-bit is unable to take a decision, and the file stops, but not crash. That's all. My initial slide deck was much bigger, so I released an extended slide deck first with explanation. So if you need to remember what this guy said or anything, and which many more examples. So I released both the slide deck for the presentation and then the extended slide deck. Thank you for your attention.